So today we're going to cover momentum. We've covered conservation of mass, conservation of energy. We talked about Manning's equation, that empirical relation for open channel hydraulics that's very commonly used and you're definitely going to see on the FE exam. And we'll finish up with the last of our conservation expressions, conservation of momentum. So as a review, we went over the basic forms of the conservation of momentum expression for open channels, and here they are. M1 equals M2, where we defined M as the cross-sectional area times this HC factor, which is the depth to the centroid of the area, plus Q squared over GA. And of course, our basic relationship for conservation of momentum, sum of all forces is equal to Q times rho times V2 minus V1. So we're going to start off with a nice derivation to see where this comes from based on this. We've seen this relationship before. We worked with it last semester. We're familiar with that as our conservation of momentum expression. So we're going to take this and see where this comes out of our basic relationship, which of course assumes steady, uniform, incompressible flow along a streamline. Okay. So momentum expression. If we have our channel in profile view, water surface, up at the top here. Your control volume. We draw around some section of this flow. Downhill gravitational forces driving the flow in open channel. And we can derive our momentum expression based on our general form of momentum equation, conservation of momentum equation. Sum of all forces is equal to Q rho V2 minus V1. And now we can go through and identify all the forces that are acting on this control volume. So what forces do we have? Let's start there. We're going to start on the sum of forces side here. So what forces do we have acting on our control volume? Colin, what do you think? What forces do we have? Yeah. Imagine this block of water, basically. Yeah, gravitational forces. We've got acting W equals mg, and there will be a portion of it that's acting along the channel. What else? What other forces? Yeah.
You see friction.
Yeah, absolutely. Friction. We have a friction force opposing the flow. As you recall, if you think back to when we were talking about pipe flow, remember the shape of the velocity profile in pipe flow was parabolic because you've got friction opposing the flow along the pipe walls. Basically, the same thing here. Well, what would the velocity profile look like in open channel flow? Is it going to be in pipe flow? We had this velocity profile like this, remember, right? What's it going to look like for an open channel? Does it look the same as pipe flow? No, why not?
No friction on top now, so it'll look like half of it.
Very good. We've got a velocity profile that looks something like this for an open channel. Because we've got that friction opposing flow at the channel bottom. The friction is essentially negligible at the interface between the water surface and air. They're open to the atmosphere. So tau naught is the shear force due to friction. What else? What other forces are acting here? Think back to those momentum problems we looked at last semester, summing forces in pipes, and there was another force we considered. What is it? What is the force that's going to act here and here? What is this? What is the thing that we neglect when we're looking at a large reservoir open to the atmosphere, when we're doing our Bernoulli's or conservation of energy?
Pressure.
Pressure, yes, pressure forces. We have pressure forces acting here, right? FP1 and FP2. And actually, those are the only ones we're actually even going to consider in our derivation. We're going to neglect the weight. We're going to neglect the shear force. And often we do that either because they, in fully developed flow, they're basically going to be negating each other, or that they are very small in comparison to the pressure forces. So that's why we neglect them. So we neglect gravitational and shear forces. And our sum of forces in that case, also I should make sure I draw on here, our X and Y are with the channel bottom, right? So our sum of forces in this case is FP1 minus FP2 equals Q rho V2 minus V1. And how do we find force of pressure? Pressure force is equal to what times what? I'm asking y'all to go pretty far back here. Who remembers? How do we calculate pressure force? pressure times area, right? So we'll have P1A1 minus P2A2 equals Q rho V2 minus V1. And in this case, since we are calculating the resultant pressure force from this entire pressure profile from the very top to the very bottom of the channel, we take half of that in our rectangular channel. So for a rectangular channel, this pressure force PA1 becomes P, we recall, of course, is rho GH or gamma H, which we'll use gamma Y for depth. We take half of that because it's a triangle, right? And we have a rectangular channel. So for our rectangular channel, this P1A1 is going to be equal to gamma Y1 over 2A1. And we'll make the same substitution for P2A2. And again, note, this is for rectangular channel. Different channel shapes have different relations. So substituting that in, you've got gamma Y1 over 2A1 minus gamma Y2 over 2A2 equals Q rho. And if we rewrite this in terms of Q's, our V2 minus V1, then we've got Q2 over A2 minus Q1 over A1. And what is the relationship between Q2 and Q1? Carly? They're equal. They are equal by which governing equation? Conservation of mass. Yes, by conservation of mass, Q1 equals Q2. So we rewrite some stuff. We can say gamma Y1 over 2A1 minus gamma Y2 over 2A2 equals rho times Q squared over A2 minus Q squared over A1. And we do a bunch more rearranging here. And we can substitute in for this gamma, or substitute in for rho, we can substitute in gamma over G, because rho G is equal to gamma. So just a little rearranging there, we can put in gamma over G for rho. And then these gammas drop out on both sides. And we're left, after all that canceling out, we're left with Y2 or Y1 over 2, A1 plus Q1 squared over, which we just said they're equivalent, so we don't need that one, but Q squared over G A1 is equal to Y2 over 2 A2 plus Q squared over G A2. And now this starts to look something like that M1 equals to M2, where M is equal to H C A plus Q squared over GA, right? Starts to take that form. Because HC, we said for a rectangle, is y over 2. So that's what this is. We derived this specifically for a rectangular channel. And different channel geometries, again, rectangular channel. Different channel geometries are going to have different relations. So that's the tables that I shared with you all last time and share with you again. Since we have different, so for different geometries, we have different centroids and areas. So we reference the tables. Table 5.1.2 and the PowerPoint table I gave you out of the other textbook because I really like that table. Table 3.1 out of STERM, which is an entire open channel hydraulics textbook that I used for a grad class a few years ago. Very nice table. Okay. You can see how you can jump right to the relationship. You can also see where this came from out of our conservation of mass or conservation of momentum expression. Any questions on that? Or anything you would like clarified? Let's jump back over to our PowerPoint. And again, here's the tables, so you can see the areas that are given for the different geometries. This STERM, your textbook doesn't just have this, but this gives you that M relationship for rectangle, trapezoid, triangle, circle. Circle one's especially nice. That one's a real. I've gone through that derivation, and it's fun. It's fun. But jumping right to the momentum expression is quite handy. Okay, so where this is useful, our momentum relationships are useful for several applications. Anything where we're trying to find out force. We're going to look at an example a little later on a sluice gate in a channel and figuring out what's the force that's acting on that gate. And it's also useful for determining water levels upstream and downstream of a hydraulic jump. I'm going to play a video for you all of a hydraulic jump. And you've probably seen these. No pun intended. Pun intended. Okay. So how many of you have seen a hydraulic jump or know what I'm saying when I say this? Have you? Yeah, maybe. No, not so much. Not seen this in other places. So this is a hydraulic jump. You can see it's traveling upstream in the channel. And what you have happening is upstream of this hydraulic jump, we have one flow condition, and downstream of the hydraulic jump is another flow condition. One is supercritical, one is subcritical, which is the supercritical flow. Just to remind ourselves, what are the characteristics of supercritical flow? Which is our supercritical flow, upstream or downstream? EJ, which is supercritical?
The one that's upstream.
Upstream. That is shallow, fast-moving flow. Then we have that hydraulic jump happening. And then downstream, we have subcritical flow. It is, relatively speaking, deeper and slower than our upstream supercritical flow. So we can figure out what the relationship is between these depths of flow using conservation of momentum. And this is really handy because we'll take a look at some graphs here. If we were to draw the specific energy chart, specific energy diagram for what's happening in a hydraulic jump. You have Y versus E, your one-to-one line. You've got this curve, and you've got, we're gonna have a good bit of space here, so leave yourself some space to draw 3 diagrams right next to each other. Specific energy diagram. And then we will draw a picture of what's going on in our hydraulic jump. Okay, so we have a hydraulic jump happening. Here's our channel bottom. We'll assume it's pretty flat. And we've got supercritical flow, and then hydraulic jump, subcritical flow. So we're going from Y1 we'll say is down here. Oops. Lost our. Why are we disappearing? We want to stay here. Y1 down here to Y2 over here. And this isn't just a matter of my bad drawing here that these Y1s and Y2s are not in a straight line. We draw a line straight up like this. They don't fall in line. We go from 1 to 2, we jump, hence the name jump, from our supercritical flow condition to our subcritical flow condition, going from Y1 to Y2, not in that same energy. What's going on? Why is there this gap between these energies? What happens in the hydraulic jump itself?
The height of the water changes.
The height of the water changes, yeah. We go from the supercritical to the subcritical flow condition. In terms of energy, though, why do we not just go straight up the line from Y1 to, we'll call this imaginary point Y3? This is imaginary. Why don't we just go from Y1 to Y3?
Energy loss.
Yeah, very good. There's energy loss, all that turbulent flow happening, there's energy loss there. So we lose energy. So we go from Y1 to Y2, this is head loss. We've got head loss or energy loss in that jump. If we were to draw this out, hypothetically, this is our energy line. And in this jump, we have a loss. This is our hypothetical and conservation of energy. But in actuality, we have head loss or energy loss in that jump. So here's the part where momentum's really useful, is that momentum is conserved across a hydraulic jump. So we can use the principles of conservation of momentum to solve for the alternate depth, the sequent or conjugate depth between the supercritical and subcritical flow condition, where energy cannot be used because we have an energy loss that we can't really approximate. So our momentum diagram for the hydraulic jump . We have M versus Y versus M, depth of flow versus that momentum force expression. And this looks more parabolic, like this. Draw it a little bit lower. And in your momentum diagram, you do go right from M1 to M2. When you're traveling through the hydraulic jump. Got Y1, Y2, Y critical, right in the middle here. This is really useful. It helps us to identify what that supercritical and subcritical flow depths are, and also can help us approximate the location of where a hydraulic jump is going to occur downstream of example for a spillway for a dam, which is really important. There's all sorts of design of samples and energy dissipators to try to force that hydraulic jump to happen so that it's not happening downstream in a reverse channel. All right, so for steady flow, the hydraulic jump occurs where M1 equals M2. And these depths are referred to as sequent or conjugate depths. Which we solve for with an equation. And this is a general equation for any channel geometry. Your Y2 is going to be equal to, we can write this a couple different ways. Y2 over Y1 is equal to 1/2 times the square root of 1 plus 8 times the Froude number squared. And that's -1. And I just want to be very intentional about where that square root ends there. Again, this is general form for all channel geometries. Now we're going to take this back and look at that example problem we started last class, and we used conservation of energy to look at what was the depth immediately downstream of spillway. We've got the reservoir water surface and it's going over spillway, and immediately downstream, what's the depth? Now we're gonna take a look at, well, what's the depth of water gonna be after the hydraulic jump that we want to occur downstream of the spillway? Really example problem. Ah, there it is. Okay, so we got water flowing at the site, that same problem as last time, water flowing over a 200-foot spillway at a rate of 2,000 cubic feet per second. Depth of water upstream of the spillway is 20 feet. And we want to find the depth of water after the hydraulic jump downstream of the spillway. We did the first part of this problem last class. You didn't know you were doing the first part of this problem last class, but you did. And now we're going to do the rest of the problem. The last class, we found that the depth of water downstream was, what was it? Remind me. What did I put it? For Y1, no, Y2, Y1 is what we called it. 0.28, that sound right? Yeah, there it is, 0.28. So we found Y1 is 0.28, very shallow flow, supercritical flow condition for sure. And now we want to find what is the sequence depth. What's the depth going to be after the hydraulic jump occurs? So just to draw this out, we've got the spillway. We had an upstream depth of 20 feet. Water comes down over the spillway. Why not 20 feet? Y1, 0.28 feet. We want to find out, all right, after this hydraulic jump, now what is Y2 going to be? We can plug in to our equation for sequent depth. And solve. We've got Y2 over Y1 equals 1/2 times the square root of 1 plus 8 times your Froude number squared minus 1. Do a little rearranging. Y2 equals Y1 over 2 times the square root of 1 plus 8 times the Froude number squared minus 1. We need to solve for this. How do we do that? What's the equation? And we can use the general form or specific to a rectangular channel, since we do have a rectangular channel. What is it? Froude number tells us whether we have subcritical or supercritical flow conditions.
V over the square root of G times one.
Good, yeah. V over the square root of G times Y is our general form, or with a little bit of rearranging specifically for a rectangular channel, and I'll try to always put a little note here, rectangular channel only. It's little q over the square root of G Y cubed. We have little q from last time, 10 feet squared per second over G 32.2 times Y 0.28 feet, since we are solving for location 1, that's what that little subscript 1 is denoting. We get a value of 11.9. That makes sense? That we get a value that is 11.9? If we got a number that was 0.2, would that make sense? No, you'd have to question that, double check your calculations, because a number less than 1 denotes what type of flow? Subcritical, yeah, and we expect this to be supercritical flow condition. So always a good little check. That is consistent with what we believe the flow condition to be. And now you plug in Y2 equals 0.28 feet over 2 times the square root of 1 plus 8 times 11.9 squared. And again, just be very careful about where that square root ends. I always try to put in little tips of where I've seen mistakes in the past, so it helps. -1. And if you solve this through, you end up with your conjugate depth of 4.57 feet. You go from less than half a foot to almost 5 feet across that hydraulic jump. Pretty drastic change. That's why it's important. That's part of the reason it's important to control that flow condition and make sure it's happening in a place that's going to be safe. Okay. We are 2, 4, 6, 7. Yeah, let's go over to the lab for the next example problem. We're gonna calculate force on a sluice gate, and we're gonna set up the sluice gate in the tunnel and go through it there. So people on Zoom, we are gonna switch over and we will see you again in the other room. And everybody else, let's take a walk. Bring this tablet.
I think you're muted.
There we go. Now you can hear? Excellent. Okay. So I may turn it on, turn it off, and go back and forth between explanations, especially with you all being on Zoom and the sounds will work. We'll work it. All right, so what I'm gonna do, I'm gonna turn this on, and I want you to just observe what's happening. This is a model sluice gate. And sluice gates are commonly used in dams to control water level behind a dam. And they'll raise them to let water out underneath, and they'll lower them to let water accumulate inside of the reservoir. They're used in flood control, so they'll lower the water level right before a rain event, raise it. Some are automated, some are manual, but this is the basic setup for a sluice gate. So what I'm going to do, I'm going to turn the water on all the way, and we will maximize the flow rate in this. This gets up to about 200 gallons per minute of flow when it's all the way up. So you're going to assume that's what the flow rate is for your calculations. So Q equals 200 gallons per minute. And what we're going to do is calculate the force on the gate, the force on the sluice gate. Is something you're going to be using in the lab. So you can put demo on it here, and you'll visit this problem as well. It's a point gauge, and you can press up and down. It's a little meter on the side. Look at that in all right. So basically what you've got happening, what would you characterize this flow condition? Substrate closer. Substrate. What would you characterize this flow condition as? Supercritical. So we got subcritical flow condition, we've got the gate, and the supercritical flow condition downstream. And what we're trying to find is the force on the gate. So I'm going to draw the control volume for the problem, and then I'll shut the water off and use it. Okay? So we've got this. I'm going to go down stream a bit. And if you want to get a little closer and just, I don't know if you can see from where you are, observe kind of what's going on with this flow right here at the base of the sluice gate. As part of why I'm drilling that whole volume so far out. Okay? All right, I'm going to cut this on. And hopefully create a little point. Okay. So this is the control volume for our problem. let's go through. What we're trying to find, and then we'll set up the problem. So we are trying to find the force that is acting on and exerted by this gate. So we want to find F gate, the force on the gate. So what other forces are we going to consider in this problem? What are the forces do we have as part of our conservation of momentum expression? Some of the forces.
Wait,
We've got weight. For us, we are going to neglect this in our problem. We've got essentially a zero comma, so the component of weight that's acting in the direction that we're interested in solving is negligible. What other forces?
the water.
The pressure, right? Got this pressure. So we'll call this FP1. And downstream, little tiny pressure profile here, FP2. Okay. Now the reason I drew the control volume so far out and so far upstream here is right at the base of the sluice gate, we have a flow contraction. So when it first comes out, it's very, very shallow. And then it opens up again a bit more to our kind of consistent supercritical flow condition here downstream. So right here, if I were to draw some streamlines of what's going on, first of all, we've got, let's use a different color. We've got a lot of weird stuff happening right here, right, as water goes under here. And none of that is consistent with the assumptions we make for conservation of momentum. We assume we've got steady, uniform flow along a streamline. Right around the sluice gate itself, there's a whole bunch of weird stuff. So we don't draw our control volume like right here because all of those assumptions are violated. So we draw our control volume sufficiently far out that the assumptions of conservation of momentum are upheld. Make sense? It's a minor detail. Functionally speaking, the problem would be the same when we go to solve it, but as a consideration, there is a reason for drawing it so far out. All right, so I'm going to give you all, I'm just going to give you a ruler so you can draw, measure the upstream flow depth and the downstream flow depth, and we'll go over this in lab. And solve for the force acting on the gate. So I'll ask you to share your information with the Zoom team. For Y1 and Y2. So whoever wants to solve figure Y1 and Y2, you're welcome to be designated measure of flow depth. if anyone is really interested in using the point gauge for.
Do we need the height of the first one and then the second one?
You need the height of the depth of flow, yep, this and
This
that
one?
one, yep. And that's your Y1 and Y2.
Like 10 inches even. This one's like an inch.
Share that with everyone on Zoom so they know Y1 and Y2 for their calculations.
Y1's 10 inches and Y2 is 1 inch.
Thank you.
How to go? And then immediately everyone was like,
Did I hear a question?
Oh, there's someone walking by.
Oh, okay. The force on the gate, F8.
What were the units of Q again? 200.
200 gallons per minute.
So that has to be converted to feet.
You are correct. We will do some units conversion. How's it going on Zoom?
It's good.
There.
How many feet cubic now is 7.48?
It is 7.48 gallons per cubic foot. Yes.
Not this one.
No. Door slamming.
I'm sorry.
Oh, no worries.
I just have a question. These are the only three bedrooms we have currently in this one.
Oh, okay.
I just have the FR.
Go back to your addition. Yeah. So this, gives you journals, you can stop right here, or you can jump right down to the broad. This is your rectangular dome. So actually for this problem, we do have to search for the distance for some purpose includes applications.
You think we started with
Include all of those same things.
subtract, would you subtract that here from all the? That's it?
Yeah.
So, would you like?
So what's the question? Are you asking if you use that
Yeah,
started
we
it?
use this equation here.
No, I think you use that one. So what is it you're solving for? Let's go back to that. FT, yep. So we need some expression to turn into several forces. And if you go back to the very beginning of class, we looked at this journal theory covering momentum expression. And you can basically use the same approach, but in addition to the pressure forces, now we have the gate force as part of your sum of forces.
Okay.
It's exact same approach. That FD is included.
Are you allowed to measure the width of the channel by any chance?
Yes, very good. You can do that. Yeah.
1 foot.
Might share that information with those on Zoom as well.
So the width of the channel is 12 inches.
B, channel width.
Did we know the flow rate?
The flow rate is 200 gallons per minute. What is HC for a rectangular channel? Yeah, half the flow rate. Y over 2. Where are we on Zoom?
I'm solving for Q right now.
Okay, units conversion.
Yeah.
Q gallons per minute to cubic feet per second.
12 inches.
Final answer?
7,900 something?
That would be a lot.
Yeah, I think.
Would be a lot for this slick growth model for our channel here.
Thank you, Professor.
See ya. Clinically done. The density of water in English or US customary is 1.9 for slugs per cubic foot. You're doing that right. Use unit weight of water. You don't have to use rho, but one way of solving it. You substitute in gamma. Gamma is 62.4 pounds force per cubic foot.
Some reports of also here. That's also,
Okay. If you do need to go, you are welcome to do so. We'll go through this. I'll post the solution for this up on Blackboard so you can take a look. And there's also, when I post your homework, there's a similar problem, so you can use this as the format for it. But you should end up with about 17 pounds force in the end. Kelly's just shaking her head like, is that what I got? ultimately, that's about what you should end up with. Okay.
Hey, thank you.
Thank you.
Thank you.